All right, well, we can begin. We have very few people, but that's okay. We're all interested and it will be recorded. So let me introduce there Chris Dotson, who got his master's under my supervision these many years ago. I didn't look it up to see what year it was, but it was in the year 2000. Okay, so 21 years ago, and has had a successful continuing career at IBM ever since. And so you're going to tell us something about the cloud. And every so often, IBM comes out with new cloud stuff. So you'll tell us all about what's new.
Yes.
Go ahead. And you can share your screen if you want. It's available to you.
Sure, I will do that. I actually tested earlier and Zoom kept crashing. And so I finally figured out that if I set it to legacy mode, it wouldn't crash. So let's see if it works here. If not, it's not essential.
It looks good to me.
Great, great. So
I'm seeing two things, black on the left and white on the right.
Yeah, so is there words on the left? Because we're
it's got the title, yeah.
Okay, good. Thanks for inviting me. I was actually surprised to find it had been over 6 years since I've done one of these. It doesn't seem like that long, but I do wish we could do it in person. I'm certainly used to doing talks remotely at this point, and probably you're used to listening to them. As you said, Dr. Finkel, I'm Chris Dotson, IBM Distinguished Engineer, CTO for Public Cloud Security. My day job is to keep IBM's public cloud services secure. As you said, I got a Master's of Science in 2000. I did nearly get thrown out of the university for, let's say, unauthorized access to computing facilities a couple of times. So my job is to stop people like the younger me, although I think their motives are usually a lot more malicious in nature than mine were. And today I was going to talk a little about distributed cloud and then about cloud security, which is my favorite topic. I called it a talk, but do please feel free to ask questions at any time. I'm more than happy to make it more of a discussion and address topics of particular interest if you like, assuming I know something about them. So I do just have a few slides. I think it's usually a little easier to look at a diagram visually, but they're not super important if you can't see them. First, I got to get this out of the way. I give quite a few security talks. There's a hard and fast rule that every security presentation has to have a fear slide. So I just searched the headlines on Google News for cybersecurity breach. I pasted in some headlines. So hopefully now you're motivated to use cloud services securely. But in all seriousness, while the cloud models are a lot more secure in a lot of ways, the providers can do more at scale than most organizations can do on premises. There are some new technologies and usage models that can really cause some issues if not used correctly. And I'll talk about a few of those. Cloud services in a nutshell allow you to have someone else manage the parts of the technology stack for you. So you may be aware traditional cloud services are infrastructure as a service, which is where someone runs compute, network, and storage for you. Platform as a service, where someone runs like a platform type of thing. So something that's above the infrastructure, but is not used directly by end users, is used to create an application. Things like databases, message queues, other service mesh or other types of things. It's sort of a catch-all in the middle. And then software as a service is also pretty obvious, where someone runs an entire application for you and you just use the application. The exact classification doesn't really matter so much. It's a fuzzy area. It's just kind of good general way to think of things. The most important thing is for a given service that you know what it is, what it does, and what you're responsible for, and what the provider is. So this means a lot of times with cloud services that the actual physical machines are in a gigantic hyperscale data center somewhere. There's acres and acres of these, racks after racks after racks. You usually don't care where, as long as the latency to you is acceptable. But sometimes the latency isn't acceptable to the nearest cloud data center. I did at one point, jokingly put in a feature request to upgrade the speed of light in our area of the universe. I haven't gotten any response yet. But if you're 20 milliseconds away from the closest hyperscale data center, that works fine for most workloads, but might not for a few. So for example, machine vision things that rely on reacting very quickly. We do some work with like factories where the machine will watch, and if X happens, you need to stop the machine within a very short amount of time. Those types of things. Latency can sometimes be very important. So There are various solutions to that problem. Edge computing is kind of one way where you put compute resources in places that are very close network-wise, at the edge. So cell phone providers have compute resources hosted right in their network points of presence in some cases. So if you're on a cell phone and you want to access something, if they've got something in your local POP, it might be only a few milliseconds away. But sometimes you do need latencies on the order of a couple of milliseconds. At that point, you really have to have something on premises. What do? You like having somebody else manage parts of the stack for you, or at least, we hope you do. If you're going to have something on premises, you can't get away from doing the power and the cooling and hooking it up to the network, but you can drop in some pre-configured racks of equipment or just rack and stack your own equipment and then still get a lot of the benefits of cloud by having somebody else operate the infrastructure as a service bits that allow you to create compute resources when you need them, containers, virtualized storage, software-defined networks, those types of things. And as well, creating and keeping platform things running, so like databases, AI type stuff like speech to text, tone analyzers, vision analyzers, things like that. We have all those types of things as cloud services, or even full applications. As I said, latency is not the only reason to do this. You might be required by laws to keep your compute resources physically in a particular country. Whether you think it makes sense or not, if it's the law, you have to comply. Or you might have petabytes of data and it's too much trouble or too expensive to move that data to the cloud and keep it synced up if you need it in both places. That's basically, we call that data gravity, where the applications kind of accrete around the data like a black hole. So the answer to this, IBM's answer to this anyway, is IBM Cloud Satellite. And that lets you have some compute and network and storage resources wherever they are, on premises, on another cloud. And then IBM takes care of building up layers of complexity on top of this base and managing it. So the base substrate is compute resources that you provide somehow. The next layer up is Red Hat OpenShift. Red Hat OpenShift is an enhanced distribution of Kubernetes, which is a container orchestration system. And I don't, hopefully it's not overkill for the audience, but I will take a few minutes to describe what Kubernetes, or kubes sometimes for short is, and containers. So Kube is designed to manage a whole bunch of containers. I think I've got a slide. That's the IBM Cloud Satellite side. So Kube is designed to manage a whole bunch of containers at scale. Containers are basically just fenced-in processes. All the containers on a given host run as processes on the same kernel, but they're put into groups, and the processes can only see the other processes or resources that are in their group. So a container can have its own file system, its own users, and so forth. Anything running there kind of thinks it's running on a separate system, a little bit like a virtual machine, but instead of virtualizing the hardware, it's all done within the same kernel.
Question.
Yes.
When you talk about containers, you're talking about Docker and Singularity?
Yes, yeah. I mean, Docker is the most popular. Docker is one way to, it's actually the C groups functionality built into Linux kernels since 2.4 something, I think, or 2.6 something. And so Docker is just a program that sets up those C groups and starts processes in those C groups in the network names, sets up a network namespace and can process namespace and so on for it. It's nothing new, actually. FreeBSD jails, I think I looked up, those dated from around 1999. Solaris zones around 2005. IBM had AIX WPARs around 2007. So container level virtualization's been around for a long time, but only in the last 3 to 5 years has it really taken off. As like the way to run most things, most new things. It does have some interesting security ramifications. The Linux kernel has about 300 system calls. Actually, I fondly remember implementing a system call in one of your classes. But so 300, that's a big attack surface. If you have a security vulnerability in the Linux kernel anywhere in those 300, then anything running in a container can escape out of the container, presumably, and take over the host it's on. A hypervisor might just have a few hypercall interfaces where the guest machine's operating system can ask the hypervisor to do something, read this block, write this block, talk to the network, read the floppy drive. Interestingly enough, there was a vulnerability a while back on the floppy interface. And of course, nobody actually needed the floppy interface anymore on the virtual machines, but nobody had bothered turning them off. So a lot of things were vulnerable. So Hardening is important. Turn it off if you're not using it. There has been some interesting work in re-implementing some of the operating system calls within the container environment to limit the attack surface. Although, like right now, it looks like to me the trend may go towards just having very lightweight and quick to start virtual machines. That then that virtual machine starts up and just runs the set of containers for better isolation, as opposed to changing the container environment or the kernel environment significantly. There's enough built in to the chips now for the AMD VTX, I guess it is, and Intel, or vice versa. But there's enough virtualization stuff built into the chips at this point that a lot of that stuff can happen at nearly full speed. The net right now is that you do have to be careful of containers in multi-tenant environments, or really any environment where you're running things from different security classifications, because fundamentally there's going to be more options for breaking out of a container and affecting the host operating system than there is to break out of a virtual machine and affect the hypervisor, just because of the design of the two environments. You have these containers, and they're actually named, by the way, because they're like shipping containers. Shipping containers revolutionized global shipping by allowing things to be shipped in standard sizes and just load up the boat with a bunch of containers rather than a complex loading. Rather than a complex loading of the boat, you can just load up a host without worrying about interactions, what's in each of the containers. So very similar in that respect. These do not get stuck in the Suez Canal, fortunately, but they are very useful. So as you mentioned, Docker is a very well-known program to run containers. Docker knows how to start up processes, knows how to put them in C groups on the host, but Docker is not the only way to run them. There's actually several other container runtimes, and Kubernetes tends to use, I think, Containerd mostly, and Red Hat OpenShift uses something called Creo. But they're all the same thing. They're all just telling the kernel, hey, set up this area and then run this process in it. So you have a lot of containers. You can host them on a single machine, and it makes life a lot easier. There's no conflicts between the stuff in the different containers and so forth. And then that machine crashes and everything goes down. So it would be great to have the containers on two machines or in machines, but then that's a lot more to manage. That's where Kubernetes comes in. So Kubernetes runs an agent on each machine, bare metal machine, virtual machine, and it schedules collections of containers, which they call pods, onto multiple machines. So for example, it can always keep 2 copies of a container running. If one dies, it'll start another one. I'll tend to continue saying containers, although the correct terminology for Kubernetes is actually pods, which is a collection of containers in the same namespace. Same network namespace, I should say. So Kubernetes is actually a lot more complicated than a scheduler. And I'm frankly not the foremost expert on it, although we have a lot of them here at IBM, but I'm just going to give a whirlwind overview. Inside a Kubernetes cluster, you have a whole virtual universe, basically. So you can partition off different sets of pods into different namespaces so they can see each other or not see each other. Based on that, you can create role-based access controls that control exactly what those roles, which can be assigned to an entity like a machine or something, or an actual person. You can just control what those roles do, either to the cluster as a whole or within particular namespaces. You can create software-defined networks within the cluster so that you can talk on various ones. By default, like every worker node gets its own overlay network that lives right within there, and then the Linux operating system can just NAT stuff in and out of that overlay network. And you can create ingress controllers like proxies to send information to a particular pod running somewhere in the cluster, and load balancers to distribute the load across multiple pods, and what's called node ports, which is basically a NAT in. Every node in the cluster opens up port like 8080, and if you hit port 8080, it NATs it and then routes it to the correct pod wherever it happens to be running within the cluster. So lots of powerful stuff here. You can create storage resources inside the cluster. You can create what's called volume claims. So you can say, I need this particular type of thing, and it can be carved out of a pool of storage for you, which is backed by an NFS server or ClusterFS or Ceph or whatever. It's a very modular thing. You can plug in storage providers. You can plug in network providers. Lots of great stuff there. You can create new secrets, like an API key to an external resource. And then you can control access to those secrets so that the pod that need to have the API key can see it, and the others can't. And so there's a huge problem, has been for many years now. It's nothing super new, but there's a huge problem with secret sprawl, secrets being all over the place in lots of stuff, and particularly people having secrets in source code and then accidentally checking that source code into GitHub, and there's bad guys that watch for that and start using them in a matter of an hour or two in a lot of cases. And so the best practice at this point is to keep all your secrets in a vault, and then as you do your build, you pull them out of the vault, you push them into, like in this case, Kubernetes secrets. They can be, they're not stored on disk or anything, they're just held in like RAM disk, TempFS or something, and the pod can access them and nobody else in theory can. So you can also within Kubernetes define custom resources. So you can say, you can teach a Kubernetes cluster how to create like a Postgres database, for example. And then you can have applications say, when I'm starting up, I need a Postgres database, and it can create one for them and keep it running. And then the different application pods can be stateless and just refer to that database. They can live and die and everything, and they can always keep the stateful Postgres database up and running with, backed by, a highly available backing store, again, like highly available NFS servers or something like that. So behind the scenes, when you create a custom resource like that, it can create the pods and services and load balancers and all that stuff needed to run that highly available database. So Red Hat OpenShift is a version of Kubernetes with quite a few extra features. You get a container image repository with it. You get a built-in way to create container images from source files and move them on through the process. So for example, you can commit code to your source code repository like GitHub, and then that automatically triggers a build process, and that creates a container image and maybe a deployment to a test environment and running some tests, and then ultimately deploying it to production. Another part of that is OpenShift service mesh. I don't have that on the diagram here, but a service mesh is another layer of abstraction that goes on top of the Kubernetes orchestration, and that lets the platform do more for you. In this case, it adds a little sidecar or an additional process to each container to control traffic for security and performance reasons. I really like this for the security implications, of course. The sidecar acts as a transparent proxy, basically. And so you can make, your application can make what it thinks is a regular HTTP connection. It gets caught by the sidecar, intercepted, and turned into an HTTPS connection with mutual TLS. So if component A wants to talk to component B, it just says HTTP://container B, component B. The Kubernetes resolves that to an IP. The sidecar automatically has its own TLS certificate and private key. The destination has its. They verify each other on the network. It could be going just on the same machine, or it could be going across the world. A Kubernetes cluster doesn't have to be regionally located necessarily, and it's all TLS, 1.2 with mutual TLS, and the application writer didn't have to worry about any of that. So without your application knowing anything about it, all the connections between things in the cluster, at least, are automatically secure from snooping or tampering or man-in-the-middle attacks. You can also use an egress feature of the service mesh. So you define exactly which URLs your container needs to talk to. And then the service mesh enforces that. So it says, well, you're only allowed to talk to this proxy, this forward proxy, and the proxy is configured to only allow out things that are on the list of things it's supposed to. Egress controls are really useful. Like if you look at the recent SolarWinds hack, egress controls are one of the few things that could have blocked that attack. The malicious software still would have been downloaded because we trusted SolarWinds. It would have run, but then it couldn't have contacted its command and control server for instructions. It couldn't have opened a backdoor available for people to get to, or it couldn't have exfiltrated data. So it's pretty limited at that point if it's not allowed to talk out on the network. But egress controls are pretty painful in a traditional virtual machine environment. I generally would recommend them for really high security environments, because someone has to set up a proxy and maintain the rules list, and then every application has to have credentials to talk to the proxy, and then the proxy has to be manually configured to allow those particular URLs through and block all the rest. And it's a bit of a maintenance nightmare. With Kubernetes and Istio, or with Red Hat OpenShift and OpenShift service mesh, you can simply declare what you want in code, and then the platform enforces it. It's a lot easier for both the application developers and the people running the infrastructure. If a next version of your component needs something else, you code that in, it goes through your processes for validation and so forth, it gets pushed out, and the appropriate configurations. It's declarative in nature, so the appropriate configurations get made. This certainly doesn't mean that there are no attacks possible. If you can make the system run an application, then you can define that it should be allowed to talk to your command and control server, but it does limit certain types of attacks around taking over an existing application, right? It certainly doesn't handle all threat vectors, but it handles a number of them. So you've got this whole new world built around everything is code. You've got a complex platform that can take a lot of the work out of development operations. It's basically another layer of abstraction. And I don't need to tell you all, in computer science, abstraction layers are a good bet if they're doing something useful. I think the quote is, all problems in computer science can be solved by another level of indirection, except for too many layers of indirection. So in this case, Kubernetes and OpenShift lets people package up workloads, applications, or platform services or whatever into a container or a set of containers, lets them deploy them and manage them in a lot of different places in the same way. That platform, Red Hat OpenShift, is what runs on IBM Cloud in IBM's data centers, or using IBM Cloud Satellite anywhere else. You can install third-party software onto OpenShift, like IBM Cloud Packs are the way the software is delivered now. So you just install that, and then that teaches the cluster how to create all these different custom resources. And then you ask the cluster to create an instance of a Java application server, for example, or of a database, or of one of the Watson AI services, or the QRadar security information and event manager, or whatever. As part of building your overall system, you can just have it create multiple instances of that and software define what talks to what and all those lovely things. And of course, you can create your own container-based applications and deploy them as well. IBM can manage the cluster itself from the cloud, keeping it running and healthy, providing minor fixes automatically. But as I mentioned, there's kind of a catch, since it's a very useful layer of abstraction, but it has its own requirements for security. And if you ignore them, then bad things can happen. I do want to take a minute to talk about the shared responsibility model in cloud. This is a big thing for all cloud providers. So if you're coming from an on-premises environment, you usually don't have to worry that much about who's responsible for what. Either you give the application to an application team to run, and then they run everything, power, cabling, all the way up to the application, or there's an easy way to see the line between the application and the infrastructure, and the roles are fairly clear. With cloud, it can be a little more complicated to figure out whose job different things are. This isn't anything really new, but there are a lot more distinct layers, and a lot of times multiple different providers, and in many cloud environments, and people often get confused on who's responsible for what. One example I like to give is that a lot of big mistakes people make, thinking that if you rent a virtual machine from the cloud provider, then the cloud provider will patch the operating system. And that's not the case. Like, it'll be in good shape when you get it, but it's kind of like buying a car, renting a car, right? It's in good shape when you get it, but if you drive it into a tree, that's on you. So the cloud provider is going to patch the hypervisor underneath it, but for most infrastructure as a service, you as a customer have to patch the virtual machine's OS. This is kind of scary. I mean, I've got this statistic here. At one point, Barracuda Networks, I think it was a few years ago now, did a survey and found that 77% of people thought that the cloud provider was responsible for basically everything. And the cloud provider will tell you in terms of service and everything that they're basically selling you tools and services, but you've got responsibility to do a lot of that stuff, depending on the tool or the service that's being sold to you.
So what does protecting the data mean here? Does it mean making sure it doesn't disappear, or making sure that no one modifies it who shouldn't? Because I've got data on the cloud, and I'm certainly hoping that someone's backing it up, because I'm not.
Yes. So confidentiality, of integrity, and availability, all three of them are typically what's let into protection. You want to make sure nobody's looking at your stuff. You want to make sure nobody's tampering with it, and you want to make sure it stays available, stays online for you, that you can use it. For a cloud service that's just storing files, they will give you confidentiality in that only the people that you allow to access it will have it, but it's still up to you to allow the right people to access it. If you send somebody, for example, with Google Cloud, Google Drive, if you send somebody a link that says anybody with the link can read this, and then they forward it around, you may not know who can access it anymore, and that's on you, because you shared it in that fashion. But if you've done that part right, then they have the responsibility to make sure that no people that you haven't authorized see it, including their own employees. Likewise for integrity, and then for availability, yes. I mean, they write in there, for that, they write that we are going to give you X amount of availability and X amount of durability. Availability meaning it's online for this, this 99.995% of the time, and durability of 99.99999% of the time, meaning only one time in 10 million will they actually screw up so badly that they lose the data, but maybe 5 times in 10,000, or a few minutes a year, they might have an outage that causes you to be temporarily unable to reach it. So it's all in the terms of service of what you're using, right? And they're very specific in a lot of cases to, like, it's relatively easy with file storage, but it gets a lot more complicated when you're talking about like running a Kubernetes cluster for you. What exactly, where exactly is the responsibility, and where is, what do you do as a customer versus what do we do as a provider type of thing. Thanks. I actually use a kind of a dumb analogy. Sorry if it's a bit simple for this audience, but I kind of like it. If you want pizza, you've got a decision to make, right? Do you want to make it, or take and bake, or get delivery, or go out? If I make it, I've got to do everything myself, but I get the most flexibility. If I take and bake, then I, get the dough and the sauce and the cheese and the toppings, and I just have to use the oven and provide some drinks and a place to eat. If I get delivery, then I don't have to use the oven even, which, given some incidents in the past, is probably a good thing. If I go out, then almost everything's done for me. I do still have to eat responsibly. If I choke on my food, that's a really bad outcome. It's not the restaurant's fault, barring some sort of weird negligence, right? So in the real world of cloud, that kind of maps the same type of way. Make it home is a little bit like on-prem, which isn't on this chart, but you do everything yourself. You're not using the cloud. If we map to the rest of the cloud models, then in all the traditional cloud models, the provider is completely responsible for, things like keeping the doors locked and security cameras and fences and things like that on physical security. And then also for the hypervisors, like the virtualized infrastructure. Now, IBM Cloud Satellite changes just a little, because you may actually be running like this part and this part yourself, and then you may get these platformy things run for you above it. So it gets, the infrastructure line gets split up a little farther, with different providers in play here. For IaaS, you'll notice like the network's a little blurry, because the provider will generally create the underlying underlay network, as they're called, and the switches, but then you as the customer, you've got to put in the logical network controls. And for IaaS, you've got to do the OS security, as I mentioned. You've got to do patching and logins and all that fun stuff. If you're using a platform offering, over here, then, like an application server, a database, it's going to have its own access and vulnerability management. And then your application itself, you need to make sure it doesn't have SQL injection attacks and things like that. And then finally at the top, this is the data access security, what I mentioned, like sharing files or, eating safely. You do have a certain amount of responsibility for using it safely, even in the highest level of, like software as a service. Nothing's going to save you. It doesn't matter how secure the underlying infrastructure or platform or software as a service is, if you don't, use it properly. Is kind of the recurring theme here. So access control is important at all levels, even with SaaS, and you're going to have some responsibility there. Almost every cloud provider does lay this out. It's usually pretty similar. The trick is that a lot of services don't neatly fall into IaaS, PaaS, or SaaS. Particularly the line between IaaS and PaaS is pretty blurry, as I mentioned. But it doesn't really matter which bucket you put something in. The important thing is to know for each particular service where the provider's responsibility stops, where yours starts, and if there's multiple providers, which one's doing what. Like you might have an infrastructure as a provider doing part of it, and then a separate software as a service provider doing something else, and then you as the customer. But I've seen models where there's 3, 4, 5 entities involved in some cases, and you just have to keep straight who's doing what. If there's a misunderstanding, then it's almost always the cloud consumer's problem eventually, because it's the cloud consumer's data and security incidents and things that get in trouble, although the cloud provider tends to take some heat for it too. So This is just a model of the system. I think another quote goes that all models are wrong, but some are useful. It's obviously not as cut and dry as this makes it out to be. You just have to understand the specific cloud services you're using and who's responsible for security and what parts of them, but I think conceptually it's useful. So Kubernetes clusters provide compute resources. So they're a little bit like IaaS and a little bit like PaaS, platform as a service. In the IBM model, IBM will make sure that the systems hosting the Kubernetes controller are secure. It'll perform minor non-breaking updates automatically because it's something that can be done without affecting the availability of it. But then you have the responsibility to test and push the button to update the controller for major versions, for example. And then IBM, in our model, we also provide the base operating system images and updates to those worker nodes. But since it's disruptive, potentially, you have to usually tell the cluster you want to drain everything off of there, and it starts up new copies as needed to keep the requisite number of copies. And then you can wipe out that machine, rebuild it fresh, and then migrate the containers back onto them. And load balancers and so on take care of getting stuff to the right locations, kind of in without dropping the load on from the customers. Now the Kubernetes controller itself, you can talk to it, and if you have privilege there, then you can take over any application running on the cluster. So that's obviously a concern. In an old traditional model, you had a natural separation of duties. You've got a network team that runs the switches and routers and firewalls. You've got a different team that runs the hosts and so forth. And so they usually wouldn't have one person that would have access to all those things. With the container model, you often have a lot of power to define all those things as code. And that means the people writing the code and deploying it often have more authority than you'd think. I have seen a few security incidents and some near misses because someone didn't really realize that they granted a bunch of people the ability to not only deploy something to test it, but also to open it up to the internet. So the person deploying it didn't think it was, that it would be open to the internet, but they configured a node port in there. The person who ran the cluster didn't realize that they'd given them the ability to open everything up. In the past, there probably would have been multiple teams involved and forums and approvals, and it would have taken considerably longer. So you're getting a bunch of speed and agility, and you have the ability to make it just as secure, but you have to sit and do that. You have to think about it and think about what approval flows you need and so on. So you can do all that with Kubernetes. You can limit, for example, the ability to create ingresses, which are those proxy rules routing specific URL requests to an app, or node ports or load balancers. Node ports are basically NAT connections into a pod, as I mentioned. But it's not obvious that you have to do this maybe, and it's kind of a sharp knife. You can cut yourself if you're not careful. Now, as I mentioned, it's not all bad from a security perspective. I mentioned the service mesh and the ability to perform network microsegmentation easily by declaring for each component what network access it needs and letting the service mesh encrypt and authenticate the connections and allow this only what's needed. That's all great, right? I mean, that can be very useful from a security perspective to have another, extra layers of security so that if one thing fails, something else catches it. As we know, all the network protections in the world can't really help you if you've got an error in your web application. I guess a web application firewall can protect you from some of those types of things. It can notice SQL injection attacks or things like that and block them. But in general, the network controls are just there to block access, to only allow access to the things that you need, that need the access. And if one of those things that needs to be accessed has an error, the network can't really stop the attacker from exploiting it. Its primary function is to get packets to the right place. So another great trend that I'll take a minute on is shift left. So moving more security checking closer to the actual development of the component to prevent those application level errors. So for example, if you make a commit to GitHub and somebody else then reviews it and merges it, there's a continuous integration job that's triggered by the merge. And that can perform a static scan of the code you've written to see if there's any security problems, or maybe even also functional ones. I tend to concern myself mostly with security, but I will grudgingly admit it's important that the system works also. But it can spot security problems or functional problems. And if they're bad enough, for some threshold of bad enough, the process stops. The commit's rejected, and then you either have to fix it or explain to the scanner, maybe through a comment, that this is okay. That it's been looked at, and that's a false positive. Next, perhaps the job that's triggered by a commit will perform a source code analysis of the dependencies you're including. So if you're building a container image, maybe your Docker file will include different components, and one of them might have a known vulnerability. And so some products can not only flag that, hey, you're including OpenSSL version, 1, 2, 3, 4, and that has a known vulnerability, but it can actually modify the pull request to update to the newer version for you. So it might, at that point, even stand up a test application and perform a dynamic application scan, exercising the application to see if it can cause a crash or get an error message that gives too much information. You could do a network vulnerability scan that probes all the TCP and UDP ports on the resulting system to see if there's something vulnerable listening, kind of in a safe environment before you open it up to the wild internet. And after all that's complete, it may put the resulting container image into a container registry, into storage as a candidate for deployment to production. So that's like a continuous integration type of pipeline at a high level. And then you might have a continuous delivery process too, that once you've decided that you want to deploy, this particular candidate because it's got features X, Y, and Z, and we need those, or it's better, it solves certain bugs or what have you. There's continuous delivery processes, which might take that container image and scan it because maybe some vulnerabilities have been discovered in the world since it was created. And then the resulting system as part of the deployment executes some more functional tests and so forth. So there's a lot of security that can be built into the integration and delivery pipelines. The container ecosystem with IBM Cloud Satellite and online on IBM Cloud and other clouds, it's opened up a lot of very interesting workflows to drive things straight from kind of source into production, in a fairly orderly, continuous way to where you can make changes quickly, particularly and react to problems, both functional and security problems quickly. The shift left stuff gives feedback to the development team very quickly, almost immediately, and that makes it easier to fix problems. And it also reduces risk. So rather than deploying something and then scanning it and finding it has problems and fixing them, you can fix some class of problems before things ever go into production and are out there for exploitation. That of course does not mean that you don't have to regularly scan and test the production environment also. The threat landscape changes all the time, new vulnerabilities are found, and so forth. But when you've got a threat model that includes people who are highly skilled and highly motivated to get unauthorized access, like for cybercrime to steal money, but also espionage and some of the motivations, those things, among others, can really help prevent incidents or limit the impact of them if it can happen.
So let me ask at this point, interrupt you because you're, I would say, essentially almost out of time.
I think I'm done, yeah, actually. So
yeah, it seems to me that all of these extra layers are a mixed blessing. On the one hand, they abstract things that you have to get done right and make it maybe more easily accessible to get it done. On the other hand, it increases the amount of stuff that you have to know in order to get anything done. For example, you've got to know how to containerize your application. What if you've never done that before? You have to know how to configure Kubernetes. What if you've never done that before? And so the amount of knowledge you need to use all these neat new things becomes oppressive. Is that right?
Somewhat. I think, though, that you see that in almost every field, and the answer tends to be, as with most things, specialization. So you have people who are specialized in running the container, Kubernetes. You have people that are specialized in knowing how to build containerized environments. It's just like the specializations that happen with all these different front end frameworks, web application frameworks and stuff, React and all that. There's just there's probably some equivalent to Moore's law that like every n years the number of abstractions and layers doubles and the specialization required halves or something. So it is absolutely a mixed blessing. And this is, by the way, very immature. Like all of this stuff has just taken off in the last few years, and even in just the last 6 months, big changes are happening in this environment, and the rate of change is kind of staggering. Obviously, IBM likes to make money by helping people do that safely, but it is surmountable. You do have to do considerable learning on it, and again, you tend to need a little bit larger team. For some of the stuff you don't, though. Like, I run a lot of containers here at home for my kids' Minecraft servers, right? It's a very easy way to just spin up additional ones as needed. So some of it's fairly easy and accessible. It's really when you get into the enterprise level, you know, trying to keep it highly available and highly secure and everything else, that things start getting more complicated.
Which means that if I'm an individual building an application, I have no choice but to learn all these things. I really need a team of developers with a lot of specialization, which of course you have at IBM, but we might not have as we're building an application in the department for some experimental purpose.
I don't think that that's the case. Building a container image is actually relatively easy. That is just a declarative Docker file type language that says, I'm going to start with this, I'm going to add these layers on, including my application program, and then when it's started up, I'm going to start this process, right? That's relatively straightforward and very easy for an individual to grok. It's if you're building a giant orchestration system of, I want to run this across multiple regions and so on, you know, regions of the world, and keep it highly available and highly secure and so on. That's when I think, yeah, you need a team. You can't have just one or two individuals doing something like that. But running containerized apps is actually pretty easy.
Do others have questions? All right, well, I don't hear any more questions. It's a lot of material here, and I have tried to containerize things, and it's never been easy. And it's never been completely successful either. I know that Singularity has got some advantages over Docker with respect to how much permissions are available to the processes running within it. But I find that setting up either of those for my particular applications is unwieldy. And it'd be nice if I had an expert who would do it for me. But then again, here I am doing it myself. And that's why I asked that question. Well, as I said, there's lots of material here to think about. We have recorded the talk, so no one wants to go back to it later. And I'm sure if people want to actually get involved with using any of these IBM facilities, Chris can show you at least how to get started and whom to pay.
Yeah, we have some sort of, I'd have to look it up, but we
free.
have some sort of university outreach, you know, type of thing for these types of, you know, for these types of things. I don't know the details on it, but I can probably find out if anyone's interested. It's one of those things that's sort of free to start, because a lot of them are open source. A lot of the base pieces are open source and, you know, can be freely gotten. Red Hat has OKD that you can, you know, kind of install locally and play with, and then scale up from there. But yes, I'm more than happy to try and find whatever resources we have.
Great. Well, thank you very much, and everyone keep safe, and we'll see you next week at the next Keeping Current seminar. And in 6 years, I'll ask Chris again to come and give us an update.
Hopefully not like that long. Thank you very much. Thanks for having me.